Okay, today we are going to talk about another way to solve the power placement problem. Probably a simpler way, but let's be very clear about where we are. So what's a feedback control system? So you have a system, you want to change its behavior, right? You want to improve its performance. There are many examples. So the feedback, right, normally we want to use the feedback. It has a lot of advantages. It can make an unstable system stable, right? And also it can make the system more robust to disturbances. Feedback means that you have to measure the output, right? You have to compare to the desired output, then you make a correction. Okay, here I give you one simple example to show the difference between the performance of the open loop control and the feedback control. Is a very simple example, but I think it's a good one.
This is Dr. Kraus, and I wanted to create a short video to illustrate how feedback can help a closed loop system be less sensitive to disturbances than an open loop system. In feedback controls textbooks, this is referred to as disturbance rejection. And so what I'm going to show, I've got a piece of wood with a black line painted down the center of it to serve as the path or the roadway for a track-driven robot. And this robot is differential drive, so there's two motors, one on each front tire, and when we send the same voltage to both motors, this thing should drive in a straight line, and if you want to turn it, you differentiate the voltage. So if one goes down and one goes up, we would turn in one direction or the other. And so what I've done is deliberately put a lean into this roadway so that I've kind of propped it up with some other blocks of wood so that in open loop we'll see the robot, not surprisingly in the first video that I'll show, veer off because of the effect of gravity providing a kind of lateral pull on the robot. And the open loop system has no way of sensing that pull, and so it just keeps sending the same voltage to both motors and it veers off the road. And then we'll come back and look at how feedback can change that in the second part. So here is the open loop test. So this is the closed loop test, and what's happening is there's a reflectance array sensor on the front of the robot that can sense the position of the black line that's been painted down.
Remember, right? I mean, for the first example, the open loop, there is no sensor, right? There is no sensor. The speed of the two wheels are the same because they say, okay, they're driving on the straight line. But because of this, there is a wedge, right? And there is a so then it doesn't do the work. But there is no sensor, right? But for feedback control, you have to have a sensor. There is a difference, but with the help of the sensor and then with the help of the output information, then you can do the correction.
In the center of the roadway, and so as the effect of gravity, that component that's lateral to the roadway tries to cause the robot to veer down on your screen, the control system senses that in the position of the black line with respect to the front of the robot, and it will increase the voltage on the lower tire and decrease the voltage on the upper tire to try to get this thing to drive straight with respect to the line.
You try to make the output follow the desired output as close as possible. Okay, can we make the output follow arbitrary bounded signal? Or can we make the system do whatever we like? Of course not, of course not. So how do we specify the reference signal or the desired output? Then you are going to use the performance requirements to design a reference model, such that the reference model can meet all the requirements. Then we change the problem into a model reference control. So you first design a reference model, and then you try to design the controller such that, right, the transfer function from the command signal to the output follows the reference model. Okay, in order to do that, we realize we have to use 2-degree of freedom controller. We need to design 2 blocks. One is for the feedback control, right? The other one is the feed-forward controller. So the final input is the summation of the feedback control and the feed-forward control. The feedback controller, the purpose is for the power placement, but because we want to match the zeros, right? We want to follow the reference model. Therefore, we also need the feed-forward part to match the zeros. Okay, now how did we do that? We say at the beginning we assume that we know all the state variables. We design the kind of proportional control, right? And then we say, okay, even if there is a disturbance, we can also assume that we know the disturbance. We also design again for the disturbance. And then we say, okay, we don't know them, so therefore we did the observer to estimate both the state and the disturbance, and finally we design the feed-forward part. So the final part for the feed-forward one, that one is very simple. We have a formula, but much effort we spent upon this controller and the observer. Then how do we choose air? We say it's our power placement problem, right? We choose air such that the poles match the reference model. How to choose air W? Of course, that will be, this is to do with the disturbance. That will be problem dependent. How do we design the observer? Well, it is found out actually it's very similar to the power placement problem for the controller. We just try to place the poles of observer to some desired locations. How do we choose the feed-forward transfer function? This one, we say, okay, once we know that the desired zeros and we know this transfer function of the process, this is the formula we can just simply use. Zero placement is very simple. And the separation property means when you design the feedback controller and the feed-forward controller, right, those parts are completely independent. All right, let's look at more details about this procedure. The state feedback controller, that is the first controller we discussed last week. Because it's about the stabilization, we only care about the poles. So therefore, for the stabilization, which means we want to make x go to 0, right? The reference signal is 0. So the 0 minus x, that's why the controller is, there is a minus sign, because the error signal is 0 minus x, and then error multiplied by the scan. Well, with that, we get the closed loop system. We found out that the matrix has changed from phi to phi minus gamma L. Right? And then we show that if the system controllable, then the poles can be placed anywhere. We have Eichmann's formula for that. This one requires the system to be controllable, right? Controllable, because it involves the inverse of the controllability matrix. But let's say, can you solve the problem without using Eichmann's formula? Of course, that's the way probably many of you preferred, right? You use direct comparison. You say, which means that you plug in, right? Plug in the expression of minus Rx into this one. You get this one. This is how you compute the characters polynomial of this matrix phi minus gamma L. Of course, this polynomial, the coefficient will depend upon the gain L, right? And then you compare with the coefficients of the desired polynomial, right? In that way, you have a set of equations can find out error. If the system is uncontrollable, can you still place the poles anywhere? Yes or no? Uncontrollable means that some of the poles cannot be changed, okay? Some of the poles you cannot move. Okay, if the uncontrollable poles are stable, then it may be okay. We can still control the system to some degree, right? Because those uncontrollables are stable. So it will not affect the performance very much. We call such a system, even it is uncontrollable, we call it stabilizable. We can still make it stable. If the uncontrollable poles, right, unstable, then we have to think out of the box, right? We have to find out more effective way to make the system controllable. Okay, here is a simple example to show the idea, right? You have to think out of the box to figure out our way out.
It was a hot summer day in Mumbai. One of those days when the humidity is so high that you sweat like crazy. I decided to make some fresh, cool lemonade for myself. As I began, a friend of mine called, and in the process of speaking to him, I didn't realize that I made a big blunder. I ended up adding about 5 times the amount of lemon to the water than what was actually needed. God, it tasted so sour that one sip poured into the mouth of an unconscious man would probably bring him back to consciousness. Well, somehow or the other, I had to correct this now, and as much as I wanted to remove some lemon juice out of the water to make it taste perfect again, it was impossible. Because some things in life can just never be undone. There was no way to remove the extra lemon from the water, but there sure would still be a way to fix the problem. The only way to correct the situation was to add 4 more glasses of water and dilute it. And here I was. Instead of 1, I now had 5 glasses of fresh lemonade ready to be served out to 4 more people. And I think life is exactly the same. Sometimes we cannot undo some things that may have gone wrong in our life. Some wrong decisions, wrong choices, wrong investments, wrong words that we may have spoken can never be undone. Not that we shouldn't try. We should definitely give our very best. But after having done what we can, when we cannot reverse things, to still keep trying is like attempting to remove lemon from water. And I think that would be such a sheer waste of time. Instead, we should try to work on adding so many right things in our life that the wrong seems smaller than what it was earlier. When problems seem to be helplessly beyond our control, rather than simply trying to remove them, let us add positivity in our lives and change.
Well, so whenever you come to the dead end, right, you have to think out of the box. There is always another way out. So, all right, and then that's the first step. You have to know, how to solve the problem for the simplest case where you have all the state variables, but in reality we say we only have let's say one sense of measured output, right? But then we may have many state variables. How are we going to solve the problem? That's the purpose of this observer. We say we don't need to implement the sensors to measure all the state variables that may be too expensive, right? And because we have the model, That because of the model, we can try to use that model to do the estimation. So remember, observer is not a hardware. It is just an algorithm for you to compute something. I know this phi gamma c, and then I have the observer, right, in this form. Very importantly, you can compare the exact model, the true model, and the observer. They are not the same. We need to add some extra term. Actually, this extra term is the most important part. If we only use the original model, it doesn't work, right? In most of the cases, we have to add some extra correction term. That term is from the feedback, right? We say because the desired output of the observer, of course, is the real output, right? So we have the real output signal, we get the difference, that will be the error signal. We use that error signal to do the correction, and that is the key mechanism for why the observer works. Okay, in this way, we can analyze the aerodynamics, then we get the dynamic equation for the aero signals. Once again, I want to emphasize when we say, okay, when you try to solve a problem, let's say I want you to design an observer. This is the observer. This is the equation for the observer. This is not the equation for the observer. Because if you look at the equation for the observer is the algorithm. You can implement that, right? X height, right? You can start from any initial condition. Y, that's the measure signal, all the signal available. But if you look at this equation you cannot implement. You don't know the error signal because you don't know the actual state variable X, right? This is just the equation for you to analyze how the error signal will behave. Of course, then we want to make the error signal go to 0. This matrix, right? This matrix has to be stable, phi minus kc. We can make it not only stable, we can also make the pose, right, to some desired positions. Okay. Follow the same way we can derive the Eichmann's formula. Of course, if you don't like to use this formula, you can still do the direct comparison, right? Which means you get the theoretical polynomial of this matrix, phi minus kc. You compare that with the desired polynomial. In this way, you will get the gain for the observer. So finally, about the output feedback controller, remember this is the last step. You say, okay, this will be the controller you are going to use. Just replace x by x height, right? Let's say we solve a problem like this. This will be the final step. You have to write it out. You say, okay, this is controller going to use. If you don't write it out, you may lose those simple marks. But those marks, this step must be there. Like that, I know you not only know how to compute the numbers, you know the meaning of all those numbers. That's why you need them. Okay. Then we'll talk about the disturbance rejection. How do we deal with the disturbance? What is the technique? We treat the disturbance just as another state variable, right? So because of that, when we first design the controller such that we say, okay, we know all the state variables, including the disturbance. Therefore, this gain not only design again for the state variable, also design again for the disturbance error will be got. Okay. How do we design the error omega? We will try to make this go to 0, right? Such that the effect is completely eliminated, but in many cases it is not possible. Okay. What if it's impossible, right? So this is one of the problems in your assignment. Then you have to get the transfer function, right? From a transfer function, from the disturbance to the output. Okay. By Z transform, right? You get the transfer function, and we know this transfer function, of course, will depend upon the controller gain, error omega, Right? From that one, try to analyze how you can make the eliminate the disturbance. In the simple case, that's the disturbance is a constant. Therefore, you have a system, you have an input, right? The input is a constant. Is it possible to make the output to be 0? Yes or no? The answer is, of course, yes, right? You just make the DC gain to be 0. You choose your error vertical such that the DC gain is 0. That's the way to solve the problem. Okay? Any questions? Then finally, we talk about the tracking, right? In order to solve the tracking problem, we want to follow the reference model completely. Then we need to design extra one, right? Not only the feedback controller, we design the feed-forward controller. We show that the overall controller will be just the feed-forward times B over AM. Then to make it match the reference model, we just design, right, this feed-forward controller to be BM over B. But then there is a condition, right? There is a condition for this controller to work. If we want to follow the reference model completely, yes, we can follow. Finally, we can make the transfer function from the command signal to output match the reference model. But meanwhile, we also notice that the transfer function from the command signal to the input is in this form. And then in this way, we have shown that in order to make sure that the input is bounded, this B has to be stable. Right? That is a stable inverse condition. Okay? Now, if we just want to stabilize the system, right? Or we want to place the poles, do we need this condition? We don't need. It's only for very strict requirement, right? You want to follow the reference model completely. Okay. But then in all this, for the bubble method to work, right, there is one big problem. In that approach, we assume that we know the state space model, right? So what if the state space model is not available? If we know the input output model, right, from the topic we discussed, right, about the realization, we can find out the corresponding state space model, which can produce the transfer function, right? That is one indirect way. We still use the state space approach, but we just recover the state space model from the input output model. But there is another way that we can actually directly work with the input output model. So this is the subject today. And then you will see there are some advantage in just using the transfer function. When I talk about the input output model, right, that also refers to the transfer function. Okay. So let's try to solve this problem step by step. Let's state what the problem we have. We don't have the state-based model. What we have is the transfer function or the input output model, right? We want to build a controller such that the transfer function from the command signal to the output will follow the reference model. That's the objective. Okay. Let's try the simple way, right? Let's just do some algebraic calculation. We can do the open loop control. Now, just from some simple algebraic calculation, what is the simplest controller? You can put it here such that this block times this block match BM over AM. What will be the solution? of the algebra problem. What is the solution? In the numerator should be Bm times A, right? In the denominator will be Am times B. From the algebra calculation, we say, okay, this can be a simple solution. Right. If you are given this problem before you take this course, you may come up with this solution, but let's verify whether it may work. Actually, it may work, but there are conditions for that. Okay, let's derive the transfer function from the compound signal out. If we put it here, right? Then, of course, what we hope is that all those common factors will cancel out, right? But let's check which one can be canceled out, which one cannot. And using the rule we discussed, right? We say if a factor are operating on the same signal, they can be cancelled out. If are operating on different signals, they should not be cancelled out. Let's look at A. This A here, which signal is this A operating on? Common signal, you say. This signal, which signal is this A operating on? Y. So can we cancel out A? They are operating on different signal, right? No. Now how about B? Which signal is this B operating on? This B. U. How about this B? U. So therefore, should we cancel out B? They operate on the same signal, right? Yes. So therefore, the transfer function is Bm times A over Am times A. Okay, and then we know if the whole system is stable, can we cancel out A? If A is stable, we can cancel it out, right? For stable system, we can. So therefore, what is the condition to assume the output is bounded? A has to be stable, right? Okay, then if A is stable, actually you can cancel them. Then we also have to check how about the input signal here. The input signal, we know the transfer function. How do we guarantee that the input signal is bounded? What's the condition B? What's the condition B? B has to be stable, right? B also has to be stable. So if both A and B are stable, this may work. This may work. Okay? Both the system and its inverse have to be stable, but we know that's a very strict condition. Then, so therefore, to solve this problem, we have to still use the 2 degree of freedom controller. Okay, in this one, so we were going to design 2 blocks. One is the feedback controller. We're going to use S over R, right, to describe that. So this is the feedback controller. We also need a feed-forward controller T over R. So when I write out the transfer function this way, which means, okay, I already give you the items for the numerator and the denominator. Okay, so therefore S and R, they are polynomials. They are polynomials. They are not the transfer function polynomial. And also T over R, T and R, they are polynomials. In this block, you already noticed something interesting that they share the same denominator. Later I'm going to explain that, and also we can also replace it with a different denominator, but let's just put it there. Okay, let's say this is the controller configuration we're going to use, right? It involves 2 blocks. We are going to design the feedback part. We're going to design the feed-forward part. Okay, of course, we're going to discuss them in detail on how to design that. But now let's say we are given this. Let's try to do some exercise on how we practice on how we can write the transfer function using the formula we discussed, right? I think that in the first class for the basic configuration, right? Feedback configuration, we say the transfer function is the feed forward. In the numerator is the feed forward transfer function. In the denominator is 1 plus open loop. We use that formula, try to write down the transfer function for this blocks. Of course, you can use the algebraic way, right? You have a set of equations, correlated the signals. That one will be more time consuming. You will try to be familiar, right, with the simpler way or use the formula to do it. All right, let's try to first get the transfer function. Of course, overall, we want to get the transfer function from the common signal to the y output, but let's do it step by step. Let's try to figure out the transfer function from here, from this signal, from the feed forward control signal to the output. Because from the common signal to the feed forward, that is just a block. That one is easy. And also when we apply the basic formula, right, for the feedback configuration, we don't have that block. So that's what we do it separately. So let's just look at this signal, the feed forward control signal UFF and the output. And we want to apply the formula, so therefore we have to figure out two transfer functions. One is the feed forward transfer function. The other one is the open loop transfer function, right? Then we can use the formula. So first, let's figure out what is the feed forward transfer function from the UFF to output. We have a feedback, right? But feed forward means that without feedback, what is the transfer function? Please quote the answer. What's the answer? You are now at the 5th week. You should know. What is the feed forward transfer function from this one to this signal? Without feedback, of course, it is B over A. B over A. What is the open loop transfer function? Now it's closed loop. We make it open, right? We make it open. The transfer function from the input to the final output here. So what's this whole loop? What's the transfer function? We disconnect this point, make it open, right? That's the meaning of the open loop. What's then this is the input to this open loop, UFF, and then this is the output of this open loop. So what's the transfer function? This whole loop. What's the transfer function? Negative B over A times S over R. Is it negative or is it positive? Remember, here I have another negative sign. Actually, there are two negative. There are two negative. That formula, right? We say it's a bit. We know the formula for this. Let's say this is T, this is H. That formula, right, is from the negative feedback. But it's negative feedback, so it's a plus and minus. Is the feed forward over 1 plus open loop. That is the formula, right? That is formula, open loop. Here, we know, okay, we know it is, this formula applies to the negative feedback, but here is 2 plus and plus, right? So therefore, this is plus, and then this will be, I have to make it a minus in order to apply this formula, but then I have to add -1 to make it work. But here there is another -1. That's why you have 2 minus 1. Is that clear? Okay, your 2 minus 1, that make it a +1. All right, then apply the formula. Then this will be just B over A over 1 plus open loop. Then we just reorganize it, right? Then we will get this is the transfer function from the feed-forward control signal to the output. Any questions? All right, so we already know this transfer function here from the feed-forward to the output, and we also know from the common signal to the feed-forward, right? It's just T over R. Then the transfer function, of course, from the common signal to the output is just T over R times this one. But we notice there is a common factor R. Okay, once again, let's look at this R. Should we cancel out R, or should we keep the R? If you look at this R, which signal is it related? This R here, which signal? UFF. How about this R? So therefore, should we cancel out R? They operate on the same signal, right? Actually, yes. So finally, this will be the answer. So R will be cancelled out. We have this T times B over AR plus BS. And then remember, right, A and B are given, cannot change. What you can design is R, S, and T. Okay? Any questions? Now you can say the whole, procedure is quite simple, right? You only need to design 3 polynomials, right? This S over R and also this T over R, but R is given. They are the same. They have the same R. Okay, let's say how we're going to design those 3 polynomials. The first one, right? We know that S over I is for the feedback controller. T over I is for the feed-forward controller. How do we design the feedback controller? From the last week's lesson, we know that the purpose of the feedback is to place the poles or place the zeros. Place the poles, right? So therefore, this one we say, okay, we just try to use them, place the poles. Which means, right, this is the closed loop, denominator for the transfer function. So therefore, we just design R and S such that AR plus BS match the reference model, right? But then you will say, hey, the reference model is supposed to be right AN. The denominator of reference model is AN. Why do we add A0 there? I will give you one simple answer. Last week, when we designed the reference model, normally we design it using the second order, right, prototype of the second order, right, system, because we have the perfect knowledge about the second order system, right? It's step response, it's overshoot, all those things have, very clear formulas, simple formulas, right, to relate those parameters. It's easy to use the second order system. But if you use the second order system for the reference model, your reference model will be also a second order system, right? The order of your AM will be second order. But let's say you want to control a system itself is a second order. So therefore, A is already a second order polynomial. If you design this as a first order controller, then there's A times R first order means, right? First order means that the R is a first degree polynomial, Z plus something. This A times R will be a third order polynomial, right? You cannot match a third order polynomial with the AM, the second order polynomial, directly. To make them match, we have to multiply this by another stable polynomial, okay? Such that the order can match. Is that clear? So why we need this? For the pole placement controller, right? Last week we didn't use our we say we design right with the air, right, such that it match the poles of the reference mark. But here we do need to say not, because the order of the AM may be lower than the closed loop. Okay. All right. So let's say we design my R and S such that the closed loop polynomial match AM times A. Oh, okay. Now there is only one more polynomial to design, T. But remember, right, we want to match PM over AM. That's the objective. But T is a polynomial, right? Remember, T is a polynomial. T is not a transfer function. So how can we achieve this? How do we design the fit forward controller? Right? R is already fixed in this design. How to choose the T? First of all, in the reference model, we don't have this AO, right? We add this AO such that we can solve the power placement problem. We try to match the order of the polynomial. But in reality, right, in the reference model, we don't have this AO, right? So therefore, can we make this AO disappear? How do we make this AO disappear? By designing T. What should we do? We just design T using the AO, right? Remember, for the stable system, I can always cancel out. I can cancel out the stable ones. So therefore, we say, okay, a simple way to choose, I'm going to choose my AT as AO. But not only AO, I also need to choose a constant T naught. Okay. Then why do we need this constant? Because in this way, if I design it in this way, AO will be cancelled out, right? Then I have this T naught B over AM. We say, okay, this one, if I compare this one to the reference model, we know that the poles have been matched, right? There is a problem with the zeros, but let's say right now we don't want to match the zeros. Okay, let's say I already matched the poles, but I also want to make the, at least, right? If we cannot match the zeros completely, at least I want to make the d-secant be the same. Okay, the d-secant normally, the d-secant of the reference model is 1, right? You have a common signal. I want output to follow the common signal exactly. The d-secant should be 1, right? For example, right, your common signal, let's say for air conditioning, 35 degree or 25 degree. I want the output to be exactly 25 degree, matching. In this way, means your d-secant is 1. You design the reference model normally in that fashion, right? But here, we That's the reason. That's the reason we want to introduce a constant T naught, try to match the D secant. Okay, now just recall what we have learned. How do we compute the D secant or the steady state gain of a discrete transfer function? Which value should we put those Z? Z equals 1 or Z equals 0? Z equals 1. Okay, there's a difference between this and the continuous time. Continuous time put S at 0. Okay. Therefore, compute this, we know in this way, you try to make this T naught, right, such that this one equals 1. Because the D secant of the reference model, right, is normally chosen as 1. So you make, okay, I will, in this way, I match the poles. I also make the D secant to be 1. In this way, right, actually, this is one strategy, right? One strategy that how to follow the reference model if perfect matching, perfect tracking is not possible, right? Just match the poles and also try to match the T secant. In many applications, it works. Any questions on how to choose T naught and the reason for that? I want to match the T secant. Okay. So I just mentioned one simple controller, right, which you can use. I put this T as T naught over A naught times A naught. And then this will be the closed system. If we compare, right, if we compare this closed loop with the reference model, we know, yes, there is a difference. But we want the perfect tracking, right? So therefore, the question is, can we do the perfect tracking? Can we match the zeros? We need to do something. Let's say I want to match BM, right? I want to match BM. Then you can say I can put TZ as the A O times BM. Then there is a BM over AM, but B is there, right? The question becomes, okay, can we get rid of B? So you think about that, and you're going to learn that later today. That will be a question mark. And the last point is that, can we add more freedom? Remember, right, in this design, we have 2 degree freedom controller, right? Which means that we design 2 blocks. One is the feedback controller, the other one is the feed-forward controller. But in this design, you already noticed, right? In this block, for the feedback, I have 2 polynomials to design. I design both numerator and denominator. But here, somehow I only have the freedom to design the numerator, right? You may wonder, hey, can we just put design both numerator and the denominator, which means instead of T of R, I just design a transfer function, right? Which involves both the numerator and denominator. In this way, you add more freedom. Okay, let's try this way and see how it can help us, right? Again, let's do some exercise, right? This one, I already showed you how to get the transfer function, right? I mean, if you have a good short memory, you tell me what's the closed transfer function from a command signal to the output. We know, okay, this one we already, right? Computed that. We say, okay, we first get the transfer function from UFF to the output. This is the feed-forward transfer function, right, over 1 plus the open loop two loop is B, A times S times R, right? Eventually we get this one. But here, this is a transfer function from the common signal to the feed-forward signal, right? So therefore, the total transfer function should be this transfer function times this. Okay, right? Any questions? Then we say, hey, this block, how do we design the feedback path? This one is still the same. We try to match the poles, right? And also we may have to increase the order of the polynomial. So therefore we design the R and S such that AR plus BS equals AM times AO, right? AM is from the reference model, AO plus another polynomial we want I to try to match the degree of the polynomials. Okay, this is the same. Now, then if we have achieved this, we design my S and R, right, such that the denominator match the reference model. So therefore, we have this AM of AO in this denominator. And in the previous design, right, T is the polynomial, but here HFF is a transfer function, right? It can involve both the numerator and denominator. So that indeed give us the freedom. We say, okay, I just do some algebraic calculation. HFF. I design my HFF such that, right, this block times this one equals PM over AM. Design my HFF times this one equals PM over AM. It's a simple algebraic problem, right? Then I can get my HFF by solving this one. Then I get, okay, this is the design. A naught PM B times R. Such that, right, BR will be cancelled out. A naught also be cancelled out. Then we'll have PM over AM. Once again, you want to verify, can we cancel it out? If you look at this one, if I put this one as A naught PM over PR. Is it clear? Then you clearly show, okay, which signal is this PR operating? Which one? Is UFF, right? Because this is a transfer function from the common signal to UFF. Of course, this one. Then how about this one? How about this PR? Is it, this PR is it operating? Which signal is operating on? So therefore, actually, we design this will be cancelled out. So you see, in this way, I can match my reference model, right? So this is the overall picture of the degree of the design of the two degree freedom controller. We have one feedback controller, we design one feed-forward controller, just involves the design of two transfer functions. If we compare to the state space model approach, is it simpler? Yes or no? It is simpler, right? Do we need to design observer? We don't need to design observer. Because in this approach, what we It does not involve any state variable, right? We only need the transfer function. Of course, but in all those approach, there is a key question: how do we solve this? Well, we want to design my R and S such that this AR plus BS will match a desired polynomial. That is the new problem we need to solve, right? This is different from the Hall placement for the state space approach, right? That one we need the help from the controllable canonical form, right? In that one we have a very simple solution, and then we develop that to solve the general form. Okay, so this one we need to solve, but turns out that it is also very simple. This is what we call the Diophantine equation. All right, so with that, let's take a break. Then we will talk about the detail about how to solve this Diophantine equation. We have a 50 minutes break. Welcome back. So let's continue. Let's try to design the feedback controller first. So when we design the feedback controller, so the main point is that we want to match the poles. So therefore, let's just focus on this block. Then, okay, let's just look at this block. We can write down the transfer function from this reference signal to the output. So here, from this signal to this signal, and the feed-forward transfer function is just by this block times this block. And this one, open loop transfer function will be the same, right? Like the feed-forward transfer function. This is how we write the transfer function this way. And after some manipulation, right, then we will get the form of this closed loop transfer function. Now we're going to design the S and R, right? S and R such that the closed loop transfer function, right, ACL, match the reference model, okay, multiplied by A naught. Let's first work out a solution to the double integrator. For the double integrator, from the table, right, I just showed you at the beginning, the double integrator, right, that one, the transfer function for the continuous time is just 1 over s squared, the discrete time, right? There is an extra 0 there, right? But the denominator is just 1 z minus 1 squared. In this case, so let's be very clear about what is AB, right? Here, this is A, right? The B is numerator. Okay, then how we're going to design the S and R. Let's try the simplest controller first. Simplest control, of course, is proportional control. Proportional control, which means this S over R is a constant. It means that R equals 1, S equals S naught, constant. Okay, and then let's try to plug them into the expression. There are R times A plus S times B. This is A times 1 plus B times S naught. Then reorganize. We have a quadratic, or the second order polynomial, where those two coefficients, well, depends upon the parameter S naught. If we compare it with the desired closed loop, let's say a second order polynomial, and then we'll have to match, well, we have to match those two coefficients. But we have one design parameter. Can we match them? Can we design S naught to match P1 and P2? Yes or no? How many design parameters do I have? We have one. How many equations are we going to solve? Normally, are you going to have a solution? You have one design parameter, you want to satisfy two equations, right? Normally impossible, impossible. The reason is that we don't have enough freedom, right? We only have one design parameter. We need more design parameter. And of course, you are free to design any controller you like. We just increase more design parameter, which means that we just increase the order of the controller. At the beginning, we try the proportional control, which is a constant. Then let's try the first order controller. First order controller, which means that your S and R, right? S and R, now they are first order polynomials. Right, of course, because it's S over R, right? We don't need four parameters. One have three, right? One have three because the S and R the mechanism of some constant. Okay, so let's put R as a Z plus R1, S as S0, Z plus S1. If we compare it to the proportional controller, how many extra control parameters do we have? For the proportional control, we have one, right? Now we have three. So increase the order by one. How many parameters, extra parameters do we get? How many? I don't. I mean, is it a hard question? Proportional controller will have one design parameter. Here we have three. How many more extra? You don't know how to solve 3 minus 1? Or are you just tired? You have two more, right? So basically, you increase the order of the controller by one, you again get more two more parameters. Okay, because you increase the order, which means you increase the design parameter for both a numerator and denominator. You get two. Okay, then we do this calculation again, right? A R plus BS Z minus 1 squared times R, but now R is a first order polynomial. This is B times the first order polynomial. Then we organize the terms. Of course, we are going to have a third order of polynomial, right? Third order polynomial. There are 1, 2, 3. There are the three coefficients. But then we have three design parameters, right? If the desired polynomial, right, is also a third order polynomial, then we need to match P1, P2, P3. Then how many equations are we going to get? We have three, right? How many design parameters? We also have three. So we can easily compute the design parameters by solving the three equations. We'll have a solution. Is that clear? So remember, right? If you found out you cannot solve it, right, because of lack of freedom, you are the man. You can design your controller, so you increase, always increase. You get more freedom, right? You get more freedom then. But there is a question right here. I can explain right why we have to increase the order of your reference model, right, by multiplying by a naught. Here, let's say if the reference model, the AN, is a second order polynomial. Like I said, this is normally the 2. Your reference model probably is just a second order system, right? So therefore, the order of polynomial is also just 2. Now, Can you design your R and S in this way to match this AM? You compare this one and this one. You are free to design any numbers for R and S, but can you do it? You compare those two polynomials, yes or no? This is because no matter what you do, right? There is a cubic term. Here, there is no cubic term. How can you match them? Is that clear? So we have to first make the order match. So you have to introduce another polynomial, right? Such that this one can match. Because this closed loop cannot match AM, but I can multiply AM by A naught. Okay, there are many choices. In many cases, the simplest choice, simple choice, you just put A naught. Of course, A naught has to be stable, right? Z is a stable polynomial because the pole is at 0. That is a very stable pole. You put those Z, right? And then this AM times AL is Z cubic plus P1 Z squared plus P2. If you match this one, now you can match, try to design your 3 design parameters to match this polynomial. This time, can you do it? How many equations are we going to get? 3, because P3 equals 0. Okay? Any questions? Now you know, sometimes we have to add our extra A naught, otherwise we cannot match. Any questions? Now, can we match? Yes, we can. So the lesson is that the controller must have sufficient degree of freedom, right? And also you are free to design, right? So therefore, you can design enough or a more sufficient complex controller to have enough degree of freedom. Okay, now it's time to consider a general question, because that one is just to make you have a sense about how the problem can be solved, but that is just for a particular example, the double integrator, right? But how about for the general form? So here we have to consider a more general mathematical question. Given any polynomials A and B, and there is a third polynomial or closed loop polynomial, ACL, can we find R and S? This is from the controller, right? Feedback controller, such that AR plus BS equals closed loop, ACL. This is what we call the Gauss-Fenton equation, right? To derive the solution, let's just try to get the solution for the second order system. For the second order system, which means that the degree of the polynomial, right, for the denominator is second order. This A naught cannot be 0. For the numerator, right, it can be 0, right? But once it's the second order, the degree of the denominator is 2. But the degree of the numerator cannot be bigger than 2. Okay. There is a reason for that. Okay, let me show you what could happen. Let's say I have a transfer function, right? Let's say normally said, okay, the degree of B cannot be bigger than A. But let's put a simple case, right? You have a system like this. Can we have a system like this? Let's say Y equals U. If we have a system like this, if we write it out in the time domain, right? I want to explain why the order of the numerator cannot be bigger than the order of the denominator. I'll give you a simple example here. If I write out the difference equation, it will be like this. Because this is there, right, you have a if you look at this one, what does that mean? My current input depends upon my future. My current output depends upon my future input. If physically it cannot happen, right? The future cannot affect the present. Is that clear? So that's the main reason. That's the main reason. That's what we call this is not a proper transfer function. Okay. Clear this. So that's when I say second order system, right? We refer to the order of the denominator, and the order of the numerator, right, cannot be bigger than the denominator. But of course, it can be smaller, right? That's not a problem. And then the closed loop polynomial is a third order polynomial. Because this one is a third order polynomial, of course, the controller will be a first order controller. Let's make it very general such that we have the freedom to design the both R and S with two design parameters. Then let's plug in the expression of all the polynomials, AR plus BS equals closed loop. Then we'll compare the coefficients. Then we will get a set of equations. Here, for example, let's say the AR plus BS, right? What is, if we multiply A times R, of course, you may notice that the coefficients for the cubic term is only A naught times R naught, right? The B times S, the coefficients B times S, coefficients for the cubic term is B naught times S0. So that's why if we sum them up, we have A naught R naught plus B naught times S naught that correspond to the cubic term. Should match the P naught. Okay? Then in the same way, if we compute the coefficients for the quadratic term, let's just do this. A times R will get a quadratic term. I will have, right, A naught times R1, but also will have R, let's say there is a R naught times A1. So we have A1 times R naught and A naught times R1. Right, there are two terms for the quadratic term. There also are two terms from B times S. You sum them up, that should equal to P1. In this way, right, we will get four equations, right? Four equations to match those four coefficients. We have four equations, right? And then, of course, we have four equations, and we have four design parameters, right? Okay, and let's put it into a matrix form. Let's rewrite into a more compact matrix form. So this matrix takes a very interesting form, right? There are four columns. The first two columns, right? The coefficients are taken from the polynomial A. This third and fourth columns, the coefficients are from the polynomial B, right? And also they are just a shifted version. So this is A naught, A1, A2, and then you just shift it, right, by one row, then just get okay, the first row will be 0, and then get A naught, A1, A2. And then, okay, this one is just R0, R1, the parameters for R, the parameters for S. Then we want to know whether it has a solution. This matrix, we have a label called a Sylvester matrix. Now you have this is the algebraic equation, right? You have a kind of AX equals B, AX equals B. This is the square matrix. Then what is the condition of on this matrix such that the solution exists? The matrix has to be non-singular, right, or invertible. Well, then of course that will depend upon, right? That will depend upon the parameters A and B. So what's the condition such that this matrix will be non-singular? Okay, and for you to see that condition, let's look at one example, simple example. Let's say this is the transfer function of the plant. This is A, this is B. In this case, A is Z plus 2 times Z plus 1, B is Z plus 1. Let's compute the closed polynomial, which is AR plus BS, right? So this is A, this is B, this A times R, right? This is B times S. But we notice that they have a common factor, right? And then we can take it out. It becomes Z plus 1 times, right, bracket, Z plus 2 times R plus S. Then we ask the question, is it possible to choose R and S such that AR plus BS match any desired polynomial? Let's make it more specific such that you can clearly see the answer. Remember, you are free to choose any polynomial R and S. Okay, then this AR plus BS, we know it is in this form. Can you design R and S such that the poles are placed at origin, Z cubic? You look at the polynomial on the left side and keep in mind that you are free to design any polynomial R and S. And you look at the polynomial on the right side. Can you tell me the answer? Yes or no? And why? Yes or no? I think it should be clear to you. Is that clear that the answer is no, right? And why? No matter how you design your R and S, on the right side, there is a root, -1, right? No matter how you design your R and S, there is always a root -1. On the right side, all the roots are 0. How can you make those two polynomials match? If they match, they must have the same roots, right? So therefore, it's impossible unless this ACL also contains the same factor, right? Z plus 1. You have that factor means, right? Z equals -1 will be the root. So therefore, from this one example, we say there must be a necessary condition, right? Is A and B should not have any common factor. A and B should not have any common factor. If they have, that common factor will be reflected in the closed loop. That common factor will always be there. Okay? So actually it turns out, right, that is also a necessary condition. And also I show you it is a necessary condition, but it also it is a sufficient condition. We only need that condition. The Sylvester matrix is non-singular if and only if the two polynomials A and B have no common factor. So A and B, they have no common factor. That's the case. I can always have a solution because this matrix, Sylvester matrix, is non-singular. Okay. Therefore, with that, actually, we have a basic solution for the power placement with transfer function. Okay. You given a transfer function, and we know that the order of the system is n, which means the degree of A is n. Okay, the order of the controller, we put it as n minus 1. Okay, let's write out the form, which means A and B is in this form. The order is n, right? A not is not 0. R and S, right? Because the order of controller is n minus 1. So this R and S, they each has n design parameters. So overall, there are 2n parameters, right? This one already gives you the answer. The order, the polynomial, right, is n minus 1 because there is a constant term. There are n coefficients you can design. So total, you have two polynomials. There are 2n. The order of the closed loop, because the closed loop is AR plus BS, this is n, this is n minus 1. The closed loop, the order is 2n minus 1. Okay. And this is the condition. If A and B have no common factors, R and S can be uniquely determined from this equation. Now, that equation will correspond to a Sylvester matrix, right, times those design parameters. So actually, because we know that the inverse of the Sylvester matrix exists, right, we can solve for the design parameters. Okay. Now let's talk about the reason why we limit the order of the controller to be n minus 1. Can we use a lower order controller? Let's say we don't have any constraint on the order of the controller. Let's try to compute how many design parameters are we going to get if the order of the controller is m instead of n minus 1. If the order of the controller is m, how many design parameters we can get? If this is m, how many design parameters we can have for R? How many coefficients? N plus 1, right? This one is also n plus 1. So total we have 2 times n plus 1. What's the order of the closed loop? A is n, right? R is m. What's the order of the closed loop? You multiply two polynomials together. What's the order of the closed loop? N plus n, right? How many equations can you get by matching this AR plus SB with a desired polynomial? Or in other words, right? Other words, how many coefficients you are going to get? How many coefficients are going to match for those for the order of m plus n? How many? M plus n plus 1, right? For polynomial, there's a constant term. So this is the number of the equations you are going to get. You are going to match all the coefficients, right? And those are the design parameters. It's like those are the number of unknowns. The number of the design parameters should be at least the number of the equations, right? Otherwise, you may not have a solution. So those 2 times n plus 1 have to be bigger or equal to n plus n plus 1. In this way, you can get that the degree of the controller has to be at least n minus 1. Okay? Easily we can show that. Then you may ask, why do we just put it as n minus 1? If you put it as n minus 1, you will get one solution, right? But what would happen if the order of the controller is larger than n minus 1? How many solutions you can get? You have infinite number of solutions. Because in this way, the number of the design parameters will be more than the number of equations. Infinite, right? But infinitely, of course, that's a good thing, which means that you can pick, you can just pick those things. You have some extra freedom, right? You can use it to satisfy some other requirements. Okay? Any questions? Okay, that's the basic solution for the power placement for the transfer function design, right? We have to solve AR plus BS equals closed loop, right? And the condition is that A and B should not have any common factor. We can always have a solution. Now let's consider other factors. One is that we want to design the controller in such a way that the order is as low as possible. We want to reduce the order of the whole closed loop. And also, of course, we want to consider the effect of the disturbance. We want to eliminate the influence of the disturbance as much as possible. Okay, let's first look at the order reduction, right? We want to reduce the order because we want to keep the order of the closed loop as low as possible in such a way that the design of the controller will be simplified. And the dynamics of the system is also easier to analyze. This is the whole configuration of the 2-degree of freedom controller. And we have already derived, right, the closed loop transfer function. Here, I just write it down from the command signal to the output. This is from the feed-forward control signal to the output and times this T over R, right? This is the closed loop transfer function, right, from the command signal to the output is T times B over the closed loop. Now, let's look at this one, and then we want to reduce the order. How do we reduce the order? Here, the main technique is pole zero cancellation. Then you may wonder, at the beginning I mentioned, right? You cannot simply cancel out the pole and zero, but there is one condition you can. That is when the whole system is stable, right? When the whole system is stable, and then you have the stable factors, you can cancel them out. Okay. So here we use the stable pole zero cancellation. Then we say, okay, if B is stable, can we cancel out B? If we want to cancel out B, how are we going to design ACL, the closed loop polynomial? Remember, right? You design the closed loop polynomial. That closed loop polynomial includes the AM, which from the reference model. And also there are some other things you can put it in, right? So you think about that. Can we design the ACL such that the B can be cancelled out? Yes or no? Yes, right? I put B as a part of the closed loop because B is stable. Is that clear? In this way, I can cancel it out. Remember, here we rely on the stable whole zero cancellation, right? Whenever something is stable, and also when the whole system is stable, we can do it. B will disappear, right? So if B is stable, we can get rid of B by whole zero cancellation. So that's a very important technique. If you have a stable inverse, you can make it disappear. If B contains both stable and unstable factor, we put a B plus and B minus. B plus means a stable factor. B minus are those unstable factors. Then we can cancel out those stable factors. We put those B plus, input B plus into the closed loop polynomial. Then we say, okay, this B plus will be cancelled out, right? You are left with B minus. Can we also include this B minus into the closed loop polynomial? Why don't we cancel out B minus? If we want to cancel out B minus, means that here is a closed loop polynomial, I include B minus there. Can we do that? Yes or no? What would happen if I put B minus into this closed loop? Is the whole system stable? Which means you have an unstable pulse in the closed loop. The whole system will be unstable. For unstable system, you cannot cancel out. Then pulse and zero. Okay? Remember, right? Let's be very clear. Let me just repeat that. Remember that your output y will be this transfer function. But there will also be which is depends upon the initial condition. Right? There's a there's a YO there. Okay. This one. This part. This part, if a system is unstable, right, this will blow up. This one will blow up. This one will. This one will also blow up. But if you have an unstable factor, if this unstable factor is the common factor, this will not blow up. The unstable factor may be cancelled out. But this one still blow up. Okay, that's the reason I mentioned, right? I mean, the common pose of those, the cancellation will affect this zero input response. Always remember that for unstable system, for any system, the output is induced by both the input and the initial condition. For unstable system and for stable system. But for stable system, this one go to zero anyway, right? For initial condition, that response always go to zero. So we'll only consider this one. But this one, we know whether you cancel it out or not, they're the same. They're the same. So, okay, that's the reason for stable system, you can cancel out the poles and zeros. But for unstable system, no, this one will be different. You cannot cancel them out. Okay, so it also means that if you include if you also include the B minus in your closed loop, you make the whole closed loop unstable. The whole system will be unstable. the signals will blow up. Okay. Any questions? So you can only cancel out of the stable factor. But this is the rule, but the other rule I mentioned, right, whether you can cancel them out by looking at association of those common factors with the signals. That one, it doesn't matter whether that factor is stable or unstable because those are some mathematical manipulation. Okay? So the answer is no. Okay. Now that takes care of the B with the we have a stable zeros, we cancel them out. Then how about stable poles? If we have a stable poles, can we also do some cancellation? Yes. So actually we can also, I can also cancel them out, which means I will put the stable factors in the closed loop. But well, if I put it there, how do we cancel them out? Of course, we have to design T, right? Because remember, you can design T. You design the T to cancel them out. Can we cancel out the stable factors and A and B at the same time? Of course, yes, right? Let's say you have those A and B that have stable factors, unstable factors. You can put all the stable factors inside the closed loop. Then, of course, you have to design your T, right, to cancel the stable factor of the poles. This B plus is already cancelled out by the factor of this B. Then eventually the closed loop will not have this A plus and B plus. All of them will be cancelled out. No. But you will say, okay, how would this cancellation affect the design of the controller? Will that simplify the controller design or not? Okay, let's look at the corresponding Diophantine equation. When we try to cancel out the stable poles and zeros. Because we want to cancel out both the stable poles and zeros, we include A plus and B plus inside the closed loop, right, on the right side. Now we write out the poles, right, into a stable pole times unstable pole, right? The B stable zero times the unstable zero. Now, when we try to design my R and S, right? And then we want to cancel this A plus times B plus. It means that both terms on the left side should have A plus times B plus. If we check out the first item, here is A plus times A minus times R. So how do we make the first term, this term contain A plus times B plus? Here we have A plus. Where do we find B plus? Of course, remember, you can design R. Is that clear? So where to find? You just say, okay, I'm going to put my B plus as a part of R. That's how you can cancel out the stable zeros. Any questions? Then how do we make the second term? Here, B plus B minus times S contains the A plus times B plus, or in other words, where do we find A plus in the second term? Of course, you say, okay, you are free to design your S. I'm put my A plus as a part of S. It seems, right, we make the problem more complicated, but no, because you already know the A plus and B plus, right? You just put it in there. What you want to figure out is just the R bar and S bar. So now let's put it in. After the cancellation, right after the cancellation, actually those A plus B plus will be cancelled out. We only have this A minus B minus in this equation, right? From A minus B minus, we want to design my R bar and S bar. But we know the degree of A minus B minus will be smaller than the original A and B, right? So therefore, the total degree of this polynomial will be reduced, right? I already give you answer, right? To this one, order of the defined equation lower than the original one, yes. So therefore, the controller design is simplified because the number of the parameters in this equation will be smaller than the original equation. Is that clear? Any questions? Okay, here let's go through one example. Here we have a problem, right? It's a second order system. In this system, we say there is stable zero. B, absolute value of B, right, is less than 1. A is bigger than 1. Therefore, this A minus B can be cancelled out. Then we have this reference model. The reference model in this way. Here I want to put a question, right? I put a reference model as Z, times 1 plus P1 plus P2 over the square. Is there any reason that I have to put this factor, right, those coefficients in the numerator? 1 plus P1 plus P2. Can we design my reference model simply as Z over Z square plus P1, Z plus P2? Can we design my reference model? The numerator just use Z. What's the reason? You try to compute the DC again. Remember, for the reference model, what's the DC again of the reference model we design? Normally, we want to put it as 1, right? Like I said, I design my air conditioning. I put my common signal as 25 degree. Of course, I wanted output to be 25 degree. If you look at the DC gain, right? Only if I put this one as a 1 plus P1 plus P2, then the DC gain will be, how to compute the DC gain? You put it there as 1, right? Okay. So I cannot simply put it in as another way. Okay, then we say that equals P is a stable zero, which may be cancelled out, right? Of course, whether you want to cancel them out is your choice. But let's try, let's say we want to cancel it out. Then let's try the first order controller first. Then we say, because we want to try the first order controller, your R, right, is already fixed. Because we want to cancel out Z minus B, and we know that stable factor will be a part of R, right? R is already fixed. Then you only need to design S. And also we know, remember, actually, that is also one typical mistake made by the students in the final exam. They say they want to have more freedom, then they just, sometimes they just increase the order of S. For example, they design a second order polynomial of S. Okay, if you do that, it also, this one it will end up with a situation that the future will affect the present, which cannot happen. So you cannot design that way. The order of the S cannot be bigger than the order of R. Okay. Then let's do the calculation, because R, right, is included, right, as Z minus B. This is A. Therefore, Z minus B will be a part of the closed loop. And then inside this part, right, is a quadratic polynomial. Then the desired closed loop, when we design the closed loop, of course, this stable zero is inside that because we want to cancel it out, right? And also this part is AN, that is from the reference model. Then we just try to match those two polynomials, P1 and P2. Right? Very easy. You can see in this design, it's very simple, right? For the first order controller, we only need to design S. And easily we can get the solution. Two equations, two unknowns. We solve for S, not an S1. Okay, and then we write down the transfer function. We say, okay, those can be cancelled out. We put approximation means that, okay, this one, right, we say, because the zero input response will be different, right? Those two there is a difference between those two, but for a stable system, they are almost the same. So how do we choose T to match the reference model? Right, here you can say, you just choose T here, by this one. In this way, you can say actually you can have a perfect tracking, right? Perfect tracking. Then this will be the resulting controller. This is the feedback part. This is the feed-forward path. But now it's expressed in terms of the transfer function. Now, here I want to mention, that you say that in the MATLAB, if you use the same link, right, you can always build the transfer function. But let's say if you want to write your own code, you want to write your Python code or C code, how do you simulate a transfer function, right? Then you have to do it, right? You have to express it out in terms of a difference equation. I want to show that. Okay, for this example, both sides are multiplied by R, right? Actually, I have an equation this way. And also I want to convert it into a time domain expression, which means Z is equal to RQ, right? The feed-forward shift operator. The Z minus B, right, is Q minus B. This is the T. This is your S. Then we can write out the difference equation, right? Time domain, this, because there is a Q, right? It is UK plus 1 minus B UK. Here is 1 plus P1 plus P2 times UCK plus 1 minus S not YK plus 1 minus S1 K. Of course, this one is not clear, right? Which signal is present and which one is in the past, right? Because now it looks like it involves both present and future. Let's just backward shift both sides. Actually, we have this one is UK. I put this on the right side. Backward shift by 1, so it's the current input can be computed from the past input right here. This is the current command signal which is given. Now this is YK plus 1, right? Change to YK. This is YK minus 1. Therefore, you look at that, then you can write a program to implement that, right? How to implement this? By programming. Of course, you just do it by loop, do it by loop. Okay, any questions? Then you know, okay, what is a transfer function? This is the way you implement a transfer function. Indeed, right, you have to do it. For continuous transfer function, how do you implement that? You have to implement through the differential equation. Okay. Now let's talk about the disturbance rejection problem. If you have a disturbance, right, we want to, right, here is just a simple example to show. You want to find a beam, you want to put the right, and then put the hand force the disturbance. It will go back to this position. All right. So now let's see how we're going to solve that, right? In this one, we have to consider the effect of disturbance. Okay. We don't need to change the structure of the control system. We still use the 2 degree of freedom controller. What we need to change is the way we design the feedback controller. Okay. Here, in the past, we haven't considered effect of disturbance. Now let's say, okay, there is a disturbance. Here we just consider the simple case where the disturbance is entering here in this position. Easily you follow the same way you can analyze other situations, right, for whether the disturbance will end here or add it to this part. The principle will be the same, right? Let's just make it simple, right? Disturbance will affect the system as a load disturbance, which means that in addition to U, right? I mean, then you say that the disturbance is affecting the output in the same way as the input affecting the output. Then let's find out the transfer function from the disturbance V to the output for the closed loop. If there are many signals, if there are many inputs, right, to the system, and then you want to find out the transfer function from one input to the output, but there are some other inputs. Okay, then how are we going to do that? Remember, I just apply the superposition principle. You know that the effect of the different inputs will be the summation, right? So you just assume the other input signals are 0. Okay, you don't consider them. Then let's just consider this one, the disturbance to the output. Then forget about those UFF, right? This common signal, assume that common signal is 0. Okay, let's just look at the disturbance and look at the output. And again, we want to use the formula, right? So let's try to use the formula to write down the transfer function. From the disturbance to the output, you look at this loop, right? It's R, right? Of course, it is a feedback path. There is some feedback, but if only without the feedback, right? What is the feed-forward transfer function from the disturbance to the output? The answer should be clear, right? From disturbance to the output. What's the feed-forward transfer function? P over A, right? P over A. Then what's the open loop transfer function? I make it open, right? Disconnect it, and then from this signal to this signal. What's the transfer function? Will be P over A times S over R, right? Once again, there are two minus signs, right? This one is up. Positive feedback, I make it negative feedback, but there is a minus sign, so there are two minus signs, which make it a positive. Therefore, the disturbance, right? The transfer function from disturbance to the output is just this one. Okay. Feed forward over 1 plus open loop. So you may say actually it's the same as the feed forward signal to the output, right? Of course, they are the same. You look at the signal, right? They're affecting the system in the same way. Okay. So overall, the output is affected by both the disturbance and the common signal. This is the effect of the disturbance. This is the transfer function we just derived here, right? This is the transfer function we also derived from the common signal to the output. Let's consider the simplest case that the disturbance is an unknown constant, which means B is a constant, but the value is not given. Then let's try to analyze the effect of this disturbance, right? If you look at this term, there is that this one is a stable system because I'm going to design. You can see that denominator are the same, RA plus BS. The closed loop, I make it stable. Therefore, the steady state output of this term will be just a DC gain, right? DC gain times the value of the input. Okay, once again, let's just recall how we compute the DC gain of a transfer function. We did it many times. I hope you remember. If you if you are given a transfer function, how do you compute the steady state gain or the DC gain? You put Z equals which value? Z equals 1, right? Z equals 1. Okay. So therefore, what's the DC gain from the disturbance to the output? Right? You just compute this one. I need to put this Z equals 1. Okay. And then the problem is I want to make the DC gain to be 0, right? Such that the effect of the disturbance, the constant disturbance, will be eliminated at the steady state. In other words, I want to design my controller such that this guy ought to be 0. But if you look at that, we cannot change B, right? So therefore, the problem becomes how we design my R such that R1 equals 0. What is the simplest way? You design a polynomial such that 1 is the root of polynomial. What does that mean? That polynomial must have a factor. Which factor? Z minus 1, right? Because 1 is a root of that polynomial, right? So you put Z minus 1 must be a factor of that polynomial. Is that clear? Okay, and then this say, okay, I'm just going to design my R in this way. That will solve the problem. Any questions? It also means that there is an integrator in the controller. You put a R, right? Z minus 1, because R is the denominator. You have a Z minus 1 in the denominator. It is like for the continuous time, you have a 1 over S, right? You have S in the denominator, okay? And we know that that is an effective way. If you want to deal with a constant disturbance, you put an integrator. Then you wonder, what about other types of disturbance? Although the disturbance is unknown to us, we can reject its influence as long as we know the key characteristics of the disturbance. For instance, is the disturbance a constant or is it a periodic signal? If it is periodic, what is the frequencies? If we know the frequencies of the disturbance, we can easily reject its effect of the system at steady state. Right? You can refer to my lecture notes for more details. Okay, once again, I want to say that's why at the beginning I give you the lecture notes. You have to read them when you try to solve the problems in my assignment. Right? You have to read my lecture notes, not only my PowerPoint slides, right? Because I mentioned I don't have time to cover all the details. Some of the details can be found from my lecture notes. Okay. So this one for other types of disturbance, you want to know the answer? Read my lecture notes. Now let's work out one example. Okay, first, right, you want to write out it's in a normal form, right? You want to know what is A and what is B. So you want to put the equation this way. Now, if I want to put the equation this way, then then we can get A and B. Where we say, okay, I just simplify the design. Let's just try to deal with a constant disturbance. If it is a constant disturbance, how should we design my R? Which factor should we put into the R? Z minus 1, right? So put Z minus 1 as a part of R. Okay, for this problem, what is A and what is B? What is A? What is the transfer function? Look at the difference equation. Can you tell? What is A? Z minus 3, right? B is 1. Okay. Then we say, okay, the simplest controller is the first order controller. But the first order controller, of course, R is already fixed. So we only need to design S. Just plug it in. So we have Z minus 3 times R plus B is 1, right, times S. So then we have a second order polynomial. There are two coefficients, but also we have two design parameters, right? We can easily match any desired second order polynomial. Okay? Can you match? Of course you can. Then we design right such that right by R and S such that the closure polynomial is T because B is 1, right? There is no B. RA plus BS is this second order polynomial. Then how about T? Because in this example, right, I didn't give you any requirement on the reference model. So if I have the reference model, of course, you can just make T to match the zeros. Now, finally, let's talk about how do we match the reference model completely, right? The perfect tracking problem. I have shown you how to match the poles. You try to design the feedback controller, right, S of R. We can match any poles as long as A and B have no common factor. And also we can also, deal with the disturbance, right? We just put those factors, some of the factors of this disturbance into R. Okay, now let's try to solve the perfect match problem. We also want to match the reference model completely. Okay, now let's look at the transfer function again. Okay, we get the transfer function from feed-forward control signal to the output. And then we get the transfer function from the command signal to the output, right, multiplied by T over R. We know that we want to match PM over AM, right? PM over AM. Now the difficulty is, in this closed loop, right, transfer function, there is a P in the numerator. If we want to match the PM over AM, somehow we have to get rid of P. But how do we get rid of P? How do we get rid of P? Can we make P disappear? If yes, how do we do that? But on what condition we can make it disappear? Can we cancel out B? If B is stable, right? We just mentioned, right? How do we reduce the order? Actually, this is where we can use that technique. We can reduce the order. If B is stable, I can make it disappear. And in that case, I just put B as a part of R, right? How do we do the whole zero cancellation? Well, how do we cancel out the stable zero? This is where we can use that technique. We put B as a part of R. In that case, the B will be a part of the closed loop. Suppose. So we choose R and S, right? Such that the closed loop, right, includes B. Because, which means AR, right, plus PS here, there is a B. And because B is stable, B will be cancelled out. If B is cancelled out, look at this closed loop, right? This one is AM times A naught times B. B can be cancelled out. Then we are left with T over AM over A naught. I want to match PM over AM. So how are we going to choose T? How do we choose T? This one is simple. How do we choose T? T equals PM. And also I want to cancel out A naught, right? Easy. See, once we use the Hall zero cancellation, and if B is stable, actually with this design, you can say I can easily cancel them out. Here, when I cancel out B, why can we cancel out B? When I say cancellation, well, we won't cancel out the two ways. One way is that they're operating on the same signal. The other reason is that is the whole system stable and it is a stable factor. What's the reason B can be cancelled out? Because, which reason? Because they're operating on the same signal or because it is stable? Because it is stable. Also, the same reason why we cancel out A naught, because it is stable. Okay? Yes. So, but now, then there's a condition, right? There's a condition that B has to be stable. Do we need that condition in the state space approach? For perfect tracking, we also need the same condition, right? Stable inverse condition. Okay. Then you may wonder, hey, is that so critical? Can we get rid of this condition by adding more freedom? Let's try that, right? So instead of T over R, we say we have another way to design, right? Let's put a transfer function instead of T over R, which means, well, I can design both the numerator and the denominator together. Okay, then let's work out the transfer function and then we'll try to match them. Then we say, okay, this one I can write out the transfer function from the feed forward to output. And this is transfer function, just the HFF. This would be a total transfer function. And choose R and S such that, or just the This time we say, because we don't want to cancel out the stable zeros, right? And we say, okay, whether the B may be unstable, so I don't put BR inside this closed loop. I just put the closed loop at AM times A naught. And we have this one. So we say, okay, I want to make this match PM over AM. So this one times this one equals PM over AM. Then I get, this is the answer for the HFF. And also at the beginning, I show you I can cancel out. I can cancel out BR because they are operating on the same signal. Let's check all the signal, whether all the signals are bounded. What's the transfer function from common signal to output now? Let's, here you can see this one, right, is the transfer function from the HFF is from the common signal, right, to the feed forward signal, right? So this P times R, right? P times R is operating on the feed forward signal. This PR is also operating on feed forward signal. That's the reason when we do this one, actually they can cancel out. Then we have that one, and then finally there's A naught and also cancel out. Then we can match the reference model. Any questions? Yes, that's no problem. Because this is the transfer function, right? And then it's from the reference model as output bounded. No problem, right? No problem. And then we have to check the input. Then what's the transfer function from the common signal to the input? Well, from those two, this is the transfer function from common signal to the output. And also we have the transfer function from the input to the output. From those two, we can easily compute the transfer function from the common signal to the input. Then you will realize here, look at this transfer function. What is the condition to guarantee that the input is bounded? What is the condition B? If this P is unstable, the resulting input signal will blow up, right? Is that clear? Because here you have a transfer function from the common signal to the input. If this one is unstable, right, of course, this transfer function will be unstable. You have an unbounded control signal. Then you say, actually, that condition you cannot get rid of, it is always there. If you want to have a perfect answer, you require this condition. Okay, is that clear? Any questions? So even if we increase the order of the controller, if we want to have a perfect tracking, we need this. Okay, let's summarize the rules for design for this approach. Okay, first of all is our comes result, right? The simpler, the better, which means when you design, when you have a choice about the order of the controller, you always prefer the lowest order. If your problem can be solved by first order, you don't go to the second order, right? Keep it simple. Also, there is a separation property. You want to design the feedback controller first, then build the feed-forward controller. The first step, before you directly solve the Diophantine equation, you better figure out what is the design requirement on R, right? Because we know that, do we want to cancel out zeros? But if we want to cancel it out, then the B has to be a part of it, okay? Then there is also a disturbance rejection consideration, right? Let's say if the disturbance is a constant, you want to input the Z-1 into a part of your R. or the disturbance in some other types, that will put some design requirements on R, okay? Then you figure out how you can design your R. So you say, okay, I have to put some factors of this and this into R. You put it in first. And then you figure out, okay, then what is the order of the controller? Here, always remember, right, the degree of the S cannot be bigger than the order of R. If it is bigger, you will end up with a causality violation, which means that the future signal will affect the present, which cannot be implemented. Okay, and then with that, okay, then you can solve the Gelfand equation. So AR plus BS equals the closed loop. Normally, when you solve that, right, you just compare two polynomials, you get the coefficients, you match the coefficients, get a set of equations. Finally, you design your T over R, right, or the HFF. So normally the last step is the simplest one. The order of the controller can be increased in order to meet other design requirements. Normally you can decide, right, the order of the controller is step 2. For example, if you say, okay, if you use the first order controller, then you realize you don't have enough freedom. Then you go up to the second order controller, right? Because you are free to design any type of controller, always, right, you will have enough freedom under the condition if B and A, right, if B and A have low common factor. And if B and A have common factors, if those common factors are stable, then no problem, right? But if there are some common factors are unstable, right, then that one is a hopeless situation that you have to find some other way out, which means the system is kind of uncontrollable. The unstable poles cannot be changed if those poles are also the zeros of the system. If you want to follow the reference model completely, you need the stable inverse condition. Okay. So let's look at a design example, right? I think in lecture 4, right, we talk about the speed control system, right? We want to control the speed of vehicle. So we consider a vehicle which has a weight, right? And then we, assuming the average friction, we design speed control system such that vehicle can reach, 100 kilometers per hour from 0 kilometers per hour in 8 seconds with an overshoot less than 5%. Okay. So we have some requirement on the settling time, on the overshoot. Okay, let's go through the design procedure for this problem again. We know that, okay, let's look at the differential equations for the dynamics of vehicle, right, from Newton's second law, right? Newton's second law, we get this one. In terms of the speed, actually, x is the displacement or the position, right? In terms of speed, x dot equals y. So actually, we'll have this my dot plus by equals the engine force, the input u. Then we get the transfer function for the continuous process. Because m is 1000, right? Here we have s, b is 100. So that is the transfer function. Okay. From this transfer function, we can get a discrete time transfer function for the continuous time. Okay. This one for the first order system, we know that the conversion is very simple. You just match the poles. Because we know, right, the poles of the continuous time to the discrete time, there is a formula you can compute, right? Then this one is easy. You can just do it by hand, right, without using the table. But anyway, the transfer function, of course, will also depends upon the sampling period. Here we'll give you the sampling period. Now, so for this system, or this is the way you can get the transfer function. You know the continuous time transfer function. You can't get the discrete time transfer function. It's a first order system. Now, how about the reference model? The reference model is built from the performance requirement, right? We say the damping ratio is less than 5% from this one. We have this formula. We say, okay, any damping ratio should be, overshoot is less than 5%. The damping ratio should be bigger than this number, which is a simpler one, right, 0.7. And then we say, okay, this is the settling time. We say the settling time is 8 seconds. We have this formula, right? We let's say I fix the damping ratio, then let's see the settling time is 8. I compute my omega lateral frequency. Okay, I put it in. Then I have this, I have the damping ratio and lateral frequency. Then I get the prototype, right, of the second order system. That will be the reference model, right? Because we know if a system follows this reference model, definitely it will satisfy the requirement, because all those formulas are precise, very accurate formulas. Of course, it is only true, right? Formulas applies to this prototype of the second order system. Okay? Then you design the reference model. You can say, when we design this reference model, it has nothing to do with the original plant, right? It is from the performance requirement. The requirement on the overshoot, on the settling time. You can say that actually different control systems may have a very similar reference model if the performance requirements are the same. Then the question, of course, when we try to build the feedback controller, we just build the feedback controller in such a way that the whole system, right, match the reference model, regardless of what the transfer function of the original plant is. Because remember, the feedback can change. Okay, now that is the reference model for the continuous time, right? Then you can use the conversion table or the MATLAB command C to D, right? Here, get the reference model. This reference model from the continuous time to the discrete time. Remember, it always depends upon the sampling period, right? So different sampling period, you have a different answer. This one you get this will be the reference model you want to follow. So here in this block, so this is the reference model you already have. Now you are given the transfer function of the system. This is B, this is A. Then you just require to design, right, the feed-forward transfer function and the feedback transfer function. And also assuming that there is a disturbance affecting the system. Okay, any questions? So you have all the knowledge. Now let's move on to the design. First of all, we want to reject the constant disturbance. If that's the requirement, how should we design the R? Which factor should be included in R? Z minus 1. It's like we have an integrator. Right? So we put Z minus 1 as a part R. Remember, right? I mean, in the simplest case, we make the first order controller, we just use Z minus 1, right? But in some case, Z minus 1 may not be enough. Once again, I want to emphasize, right? You say, I put R equals Z minus 1. If you put R equals Z minus 1, you already put a constraint that your S cannot be bigger than this first order, or the S will be S not Z plus S1. Okay. You only have two design parameters. If you realize you don't have enough freedom, once again, I want to emphasize the common mistake made by the students. They say, okay, they still keep this R. They just put those S as S square. Sorry, Z. Okay, it is S. Fine, fine. Z square plus okay, S1 Z S2 Z square plus S1 Z plus S2. It just increases the order of S. Remember, that will violate the causality condition. You have to also increase, you have to put a factor there. Let's say R0 or Z plus R0. So you have to increase the order of R as well as increase the order of S together. You cannot just increase, because remember that this one can be, right, has the order cannot be bigger than the denominator. Normally, right, remember, right, because those are the simple mistakes. Those are the mistakes you should never, right? You should never make. I mean, we students make these mistakes, which means that, okay, there's some basic principle they don't get it. That will cause a lot of, right? They will lose a lot of marks for that. Or sometimes students, they forget, they have a continuous time, they have discrete time, they remember the stability criterion differently, somehow they mixed, and then they design closed loop as unstable one. Also, if that's because that's a very critical mistake. If you put an unstable pulse in the closed loop, of course, that you violate the first principle of control system design, right? That will cause also you are going to lose a lot of marks for that. Okay. The simpler the better. For this one, right, it works. Okay, let's try the simple one. So we say, okay, Z is first order controller. First order controller, then R must be just Z minus 1. Then this is S naught Z plus S1. Then we just put it in and see whether it works. So this is A, this is R, this is B, this is S. Put it in. It turns out it's a second order system, right? Second order polynomial. And we have two coefficients and two design parameters. We can match. We compare with the reference model. There's no question, right? We can match. Easily we solve S0 and S1. Okay. So we get, so this is the design of R and S. Then how about this feed forward one? Feed forward one is simple. So because we have the formula, right? This is the formula. We have the PM, we have the R, P, and R. So this is PM. Right? We have this P, we have this R. Then we get this feed forward transfer function. Then with that finish the design. Then you can verify. So here, also I hope you have time to try to implement this in by yourself, right? Simulink, you build those blocks. Just remember, right? There is one right common mistake is when you build those blocks. Remember, you have to specify the sampling period. The sampling period of all the blocks have to be the same. If they are not the same, you are going to get some very strange behavior. Put them as the same. If you do this simulation, right, and then you will get something like this. And then when we look at this, remember we have two requirements, right? We have two requirements. Whether it was settling time should be less than 8 seconds, and the overshoot should be less than 5%. To look at the step response, does it meet all the performance requirements? Yes, right? Clearly. Overshoot is less than, remember this is 20%. This is definitely less than 5%. Settling time, here, right, here is 10. So the settling time is around 8 seconds. Okay, then in a simulation, you can verify yes, it works. All right. Okay, so that's all for today. So next week we will have the last lecture for part 1. So in the first half, I will introduce the final type of the basic controller. Right, other than in the second half, I will do a revision of all the topics we have learned. All right.